Hi everybody, so in this video I want to introduce the idea of hydrogen and van der Waals bonds. They are rather closely related, and I'm going to introduce the concept of hydrogen bonds first. And the easiest way to do that, I think, is using the molecule H2O. So let's take a look at oxygen for a moment. So oxygen has 8 protons, otherwise it's not oxygen, but it has an outer orbital that would love to bring in 2 other electrons. So even though it's got just 8 protons, it can bring in 10 electrons. And when it does so, it'll get a 2- charge. Now, the reason it likes to do that is because then it obtains a noble gas state, and that's a very stable state for atoms. So where is oxygen going to get those 2 electrons? Well, the hydrogen atom, a neutral hydrogen atom, would be a single proton surrounded by a single electron. So let's say we have 2 hydrogen atoms. So here's one over here, and then here's one over here. If we have an oxygen atom that's looking for 2 electrons, it's more than happy to pick up those electrons. And if hydrogen donates those electrons to that oxygen atom, then there are no electrons left for hydrogen. You can think of those 2 protons as just being sort of bare, unshielded protons left over here on the side of this H2O molecule. So there's the H2O molecule, a large oxygen atom that's picked up these 2 electrons, and there are 2 protons sitting out on this side. So this molecule of H2O, we would say that it's highly polar. It has a negative charge that's concentrated around the oxygen atom, which is on this side, and that's a negative charge. Then with the protons, there's an overall positive charge on this side. And so we get a molecule that is polar. And this is one of the most polar of all the possible compounds. So it's got a negative pole over here and a positive pole over here. And that strong polarity is what makes water such a good solvent. You can think of these as being little magnets that can then attack anything else that's put into water that itself is electrically charged, that these molecules can act on. Well, van der Waals bonds are really kind of a variant of hydrogen bonds, or rather, maybe the other way around is a better way to put it. Hydrogen bonds are a special case of van der Waals bonds. So van der Waals bonds are a similar idea where you have this concept of polarity. So let's take a look at the concept with a different kind of structure. We've drawn silica tetrahedra before as these little 4-sided figures where we have oxygens over here at the corners and then silica in the center. We're going to simplify that. Instead of drawing the whole 4 sides, we're going to just draw little triangles. This is often the way people draw clay minerals. So imagine a string of silica tetrahedra that are sharing corners and are bonded together like so. Now, the way that these might be attached to one another is there might be some octahedrally coordinated stuff attached over here. So what's an octahedrally coordinated fellow? Well, that would be an atom where you have 8 sides instead of 4. So imagine a little 4-sided pyramid here, and then another 4-sided pyramid down here below. And there would be an atom in the center. And let's just say, for the sake of discussion, that fellow is a magnesium. We would call it octahedrally coordinated because it makes an 8-sided figure. Now it's only attached to 1, 2, 3, 4, 5, and then back here a 6th oxygen. So it's 6-fold coordination, but it makes an 8-sided figure, so it's an octahedron. So we call it an octahedral layer. So we'll just make that an O, and then we will refer to this fellow as a T layer, since it's tetrahedrally coordinated, and it makes a tetrahedron. So we have octahedral and tetrahedral occupancies for these various atoms. Well, in the clays, it could be that the way these things are bonded, that there are some unsatisfied bonds, since there might be an overall positive charge, let's say, sitting up here because there are silicon atoms that are fully bonded but not completely shielded. And then there might be some negatively charged residual fellows down here. And if that were the case, then you could imagine you could build out another layer of tetrahedra with their positive charges that would be very weakly attracted to those negative charges. So just like we have a set of positive charges here on top of that layer of tetrahedra, you can imagine the same thing here, and they'd be attracted to those negative guys. We'll draw some more plus signs on this side, then they're attracted to that negative side. So you could build out these layers. This bond right here would be the van der Waals bonds, which is write that as VW. It is very, very weak. You can pull these apart with ease. So if you take a piece of muscovite and you start peeling across the layers, you're quite literally breaking van der Waals bonds with your hands. As soon as you peel back one layer after another, you're just breaking things along that very weak van der Waals bond.